students, today we study stationary waves. So in the first part we study formation of stationary waves and then analytical treatment to the formation of stationary waves. So we consider the example of a string. It is stretched between two rigid supports. The two fixed points we denote as A and B. If this stretched string is disturbed or oscillatory disturbance is given at the middle, then transverse wave travel in both the directions, towards B as well as towards A, in this way. This wave which we have produced is the incident wave. But what actually happens here? B is fixed point. It acts as the denser point or denser medium. It reflects the wave back. So this crest, this trough is reflected as crest in this way. Similarly, at the point A, this is crest. This crest is reflected as trough, like this. So one wave is incident. Now the other wave is reflected. So this one is reflected wave. We write here is reflected wave. Both the waves are having same amplitude, same frequency, same magnitude of velocity, but traveling in opposite direction. They form the pattern which is called as stationary waves. Why they are stationary waves? Because these waves are localized waves, because they are not transferring the energy from one point to another point. Simply points vibrate about their mean position. Some points like points P, Q, R, these points are zero displacement points. We can write here P, Q, R, A, B. Such points are zero displacement point, or for the points the displacement is zero. These points are called nodes. They are not vibrating, they have zero energy, but all other particles like particles E, F, G, H, such particles are having maximum displacement. These particles have large energy, or they vibrate with maximum energy. Such points are there, and some points vibrate having or they vibrate with amplitude or with displacement which varies between 0 to maximum. So all particles have energy except the particles at A, P, Q, R, B. Means except nodes, all particles vibrate because they have energy. But energy is not transferred from A to B or from B to A. Therefore, these waves are not carrying energy. They are not transferring energy. Therefore, they are called the stationary waves. They are localized waves. Here you have noted the point nodes, means the points for which the amplitude is 0 or displacement is 0. The points which are having maximum displacement are called here antinodes. Antinodes are the points for which the displacement is maximum. Now the portion between P and Q, or the portion between here A and P, it is called as a loop. So between two nodes there is, if we show here, point A, this one is point P. So this is called as a loop. Between two nodes there is one antinode and other vibrating particles. This portion is called as a loop. Now if we take the distance between A and Q, that distance is lambda, which is wavelength of a incident wave, wavelength of reflected wave, or wavelength of stationary wave. Here for the loop, distance between A and P is lambda by 2. For each loop, the loop length or length of one loop is equal to lambda by 2. Length of two loops is lambda. Length of two loops is lambda. You can write like this, or you can understand the portion, loop, two loops, or the whole pattern. Now we again consider our example of stretched string. One end is fixed. That end we usually have denoted by letter B, and other end is free end. It is denoted by A. It is held horizontally. It is tightly held, means it is stretched string. Now if it is continuously vibrated, then there is formation of transverse wave traveling from A to B. We can show the wave traveling in this way. This wave is incident wave. Now the point here, this wave is incident. We show it here. The point continuously vibrating here. This maximum displacement point is A, and the wave traveling towards B. Now at point B it reflects, and we observe the pattern consisting of loops. Here the wave reflected from B is reflected wave, and both the waves are identical. Amplitude and frequency are same, but they are traveling opposite to each other. Incident wave is from A to B, reflected wave from B to A. Such waves form the stationary wave. So we can define stationary wave as the wave formed due to two identical waves traveling in opposite direction. They consist of distinct loops. Now we have to show the position of nodes and antinodes by using the analytical treatment. Suppose we denote the nodes here by letters N1, N2, N3, N4, and antinodes by letter A1, A2, A3, here A4, A5. We have to show their positions, means in terms of distance x or position x, we have to form the locations of nodes and antinodes. So for that we here take the analytical treatment. So these points you have to note analytical treatment we consider by the principle of superposition of waves. You know the principle of superposition. Now we use it, we apply that principle to the formation of stationary waves. So first wave, we show its displacement from the mean position for the particle having displacement y1 from the mean position as a sine twice pi nt minus x upon lambda. This is equation number 1. Now for the reflected wave, displacement at any instant is shown by a sine twice pi nt plus x upon lambda. This is equation number 2. The first displacement we have shown for the incident wave, and second displacement y2 we have shown for the reflected wave on this pattern. Now according to principle of superposition, by principle of superposition of waves, we write here y means the resultant displacement is y1 plus y2. We substitute here the RHS. You can easily here simplify the relation by using trigonometric relations. So here this is equation number 3. Now for the simplification, we use the trigonometric identity sin C plus sin D is equal to 2 times sin C plus D divided by 2 cos C minus D divided by 2. Very simple step is there. Y is equal to, we write here 2 factor is there. A is common in both the cases, it is twice A. Now this one is sin C, this is sin D. Sin, we have to write C plus D upon 2. We calculate this bracket as side calculation. C plus D upon 2 we get C is twice pi nt minus twice pi nt minus x upon lambda plus twice pi nt plus x upon lambda. C is divided by 2. Here x upon lambda step will get cancelled. We get here 2 times twice pi nt upon 2, and we write it directly here twice pi nt. As 2 will get cancelled. Now there is cos C minus D upon 2. We calculate it inside here, C minus D upon 2 twice pi nt minus x upon lambda minus twice pi nt plus x upon lambda divided by 2, and it will be twice pi inside the 2 times, here we write 2 times twice pi x upon lambda divided by 2 with negative sign, and we get here, it is twice pi x upon lambda. C minus D upon 2. So cos minus twice pi x upon lambda is equal to cos twice pi x upon lambda. Now we write here y is equal to, we adjust the relation twice a cos twice pi x upon lambda multiplied by sin twice pi n t. This step we write here by substitution of twice pi n is equal to omega. So here we have to substitute twice pi n is equal to omega here, and for this term twice a cos twice pi x upon lambda, twice a into cos twice pi x upon lambda, we substitute it as a. Then the relation for resultant displacement y can be written as, this is a and sin omega t. So we give the number for this simplified step as 4 and the substituted step as number 5. So y is equal to a sin omega t is the equation of resultant wave. A resultant wave that is called as the stationary wave. It is also called as standing wave. Now you have to note the points starting from the displacement equation. So write down these equations and these steps, and then we take the positions by considering the equation of amplitude. So write down these steps up to the equation number 5. Now we consider a is equal to twice a cos twice pi x upon lambda. By using this equation of a, we can find out the positions. Now we have the equation number 4, we write it here. Equation number 4 we have to write here twice a cos twice pi x upon lambda and sin twice pi nt. This is equation number 4. Now in this equation we have to discuss this equation here. Here there are two ratios, cos and sin, and in cos ratio there is x means position is involved, and in sin term there is only frequency. So here in our individual displacements the relation is like this: a sin twice pi nt minus x upon lambda for the first wave. For the second wave there is positive sign. So the term or sign ratio consists of time as well as position, but in the resultant wave the term like time and displacement is absent. Therefore, here the amplitude is varying, which consists of the x or position. Here it is varying with the distance x, and here sign terms only shows the t. Therefore, the wave is not traveling, it is localized wave. From this equation 4 we conclude. So the conclusion is that as equation 4 contains the ratios like cos and sine, but not the term like nt minus x upon lambda, therefore the wave is not traveling or it is not transferring energy, it is localized wave. But the amplitude here a twice a cos twice pi x upon lambda, it is different for different positions. So for different values of x, amplitude values are also different. Now those values we have to show by two different cases. In standard cases we have to consider. So case 1 we consider for the maximum amplitude, that is equal to plus or minus twice a, means it is the maximum. We know the cos twice pi x upon lambda, this ratio is having maximum value as 1, then a is plus or minus twice a. So here it is maximum, or for antinodes we consider the case first for antinodes. So a is plus or minus twice a, means twice a cos twice pi x upon lambda is equal to plus or minus twice a, when cos twice pi x upon lambda is equal to plus or minus 1. Cos value is plus 1 when the angle is here is twice pi x upon lambda. If twice pi x upon lambda is equal to 0, then it is plus 1. When it is pi radian, then it is minus 1, and it varies like this. Then x can have the values twice pi x upon lambda is 0 when x is equal to 0. And if we take pi value, then it is equal to lambda by 2. So here we calculate like this, twice pi x upon lambda is equal to pi. If we substitute, then pi will get cancelled, x can be equal to lambda by 2. Then it is, if we substitute it as twice pi will get cancelled, we get lambda x is equal to lambda, then 3 lambda by 2, then twice lambda, like this. So position x is equal to 0, lambda by 2, lambda, they indicate the maximum displacement or maximum or the amplitude of stationary waves. So at x is equal to 0, we have here the point which is a1, it is x is equal to 0. Now if x is equal to lambda by 2, then we get the position here, it is x is equal to lambda by 2. Now then the next position is x is equal to lambda, and so on you can show in the diagram. So you have to note this case also. Then we consider case number 2. So try to note these points. Now the second case is for nodes. For nodes, node is a point which is having zero displacement, or the points on the stationary pattern with zero displacement are called nodes. So when A is equal to 0, the points are nodes. So A is equal to 0, then twice A cos twice pi x upon lambda, it is equal to 0. As twice A cannot be 0, we write cos twice pi x upon lambda is equal to pi by 2. Cos pi by 2 is equal to 0. Also 3 pi by 2 can be 0. 5 pi by 2, cos 5 pi by 2 0, and so on. It is possible if twice pi, here we have to write it 0, and twice pi x upon lambda is equal to pi by 2, 3 pi by 2, 5 pi by 2. So you can understand the mistake I have made here. If cos twice pi x upon lambda is equal to 0, it is possible when the angle is pi by 2, 3 pi by 2, 5 pi by 2. Then x is equal to, it is possible when x is equal to, we have to substitute first the value pi by 2. So when we substitute it, pi will get cancelled. We get x is equal to lambda by 4. So first value of x is lambda by 4. Then it is 3 lambda by 4, 5 lambda by 4, and so on. You can adjust the values of x or find the values of x from these angles. And we show the position of x, which are nodes, by in the diagram like this. Here the points of zero displacement we show here as x is equal to lambda by 4. We have to show it clearly. N2 is located, or N2 is at position x is equal to 3 lambda by 4. N3 is at position 5 lambda by 4. Because here between two antinodes, the distance between two antinodes here A1 and A3, this is equal to lambda. This one is lambda by 2, this one is lambda by 2. We can show it in this way. But here we have to revise again equation 4, this important relation sin twice pi nt. So this relation is important here, and from this relation we have written the resultant wave, equation of resultant wave. But this equation we have to revise many times for the discussion as well as for solving the problems. You have to remember this equation, this step. From this step we have obtained two cases. First case for antinodes, second case for nodes. Now this is about the formation of stationary wave and discussion of the positions of nodes N1, N2, N3 like this, and antinodes in terms of lambda. We have shown or we have obtained these expressions by using the analytical treatment, and we have shown for the equation 4 that equation 4 does not contain, or equation 5 does not contain the term like omega t minus twice pi x upon lambda. This term is absent in the equation. Therefore, we say that the wave is not traveling or it is not transferring energy. Therefore, it is a stationary wave. So, these two conclusions we have drawn from the analytical treatment. So, this is about the formation of stationary waves. So, today we stop at this point, and in the next lecture we discuss again the properties of stationary waves. So, thank you.